Testing, 1, 2.
Okay.
Yeah? Okay. So, seismology is going to be shared with Pierre and myself. And so I have 3 lectures this week, and Pierre has 3 lectures next week. And we tried to do some Skypes and talk about kind of the scope of what might be useful for a multidisciplinary student population. And so I'm going to start very simple today. So hopefully some of these basic things are not going to put everybody to sleep and may be useful for some of you. Feel free to stop me anytime with questions. That's more interesting to me than just me talk. And in my 3rd lecture, I'll show you here. Oh yeah, this. I will. So this is basics today, and then tomorrow will be more on modeling. And anybody wants these slides, I can give it to you on a thumbstick if you don't want to write. He does. Okay, good. And then on my 3rd lecture, I will talk about some interpretations. And this is one of my messages, is that we do some things with data, and we get a model, and then this model has uncertainties, and then we make some interpretations. And sometimes these interpretations are very poorly constrained, so sometimes they're constrained okay. And so I have some, for this lecture 3, I have, that's 2 days from now. So if any of you are really like, oh, I hope he talks about this thing or that thing, I welcome you to come and talk to me after today, and maybe I can change some slides, or if I'm not already talking about those things, I can try to include some stuff that may be of your interest. And my email is just my last name at asu.edu, and so you can come and talk to me or email me about any questions with any of this stuff. Okay? All right. So basics today. And what I put in today's lecture is kind of introduce the scales that seismology is interested in: time and temporal, spatial, sources of energy, wave paths, receivers. So these 3 are kind of a basic scope of seismology. Then I'm going to introduce data and some deep earth data. This is a deep interiors workshop. And then, like I said, we're going to go from data to interpretation. And so I kind of see it this way, where these 3 sort of go together, and then we got some data, and then we interpret it. So first, the way I like to think of seismology is just the science of vibrations, vibratory phenomena. And this is, it's not something that's unfamiliar to us. In fact, right now, right here, the ground is vibrating. There's been 18 earthquakes greater than magnitude 4.5 since midnight. And so right here, the ground is vibrating. It's vibrating everywhere. And so in seismology, we try to do something with that. So the way I think about it is the generation of the vibrations, and that's like the earthquake source or many kinds of things, and then how those vibrations travel through the medium, hopefully the medium of interest. How do we record those vibrations? We simulate, we predict vibrations, and we study the medium of which they travel through, and we determine exotic aspects of the source of the vibration. So that's seismology in my mind in one slide. And vibrations have size or amplitude. They have some temporal component to it and wavelength. And this is not new to us. As scientists, we understand the concept of wavelength and frequency from natural phenomena. in the from the cosmos to biology, and in seismology, you could think of it like a spatial, the distance between two crests, or how does one crest move in time, or in other words, if you want to think about it in space and in wavelength, so you have your distance here, or here's space, and your temporal. So you have these concepts of frequency and period, which is just 1 over frequency. So we could think about the what? I told everyone, let's start before Stefan gets here. But I've just finished talking about you. Ladies and gentlemen, Stefan Lebras. Okay, so seismologists have traditionally thought about these propagating waves. I think statistically, if you look at the number of studies, we think about time amplitude, so these seismic wave recordings, but we get into both spatial and temporal thing. And then in terms of Earth structure, which I'm not going to dwell on these things too much in this lecture, but we have scales, sometimes very, very small, meters, and it depends on what we can measure, actually. So how good are our sensors, and how good are the data, and how far away was the source of the energy. So sometimes meters, that'd be like roughness of the core mantle boundary, to thousands of kilometers, and this could be these large, low shear wave provinces. And I have a question. So the break starts at 10:15, right? Yeah. And do you want me to stop ahead of that for questions, or we stop and nobody asks me anything? Boom, coffee. As I go. Yeah. Okay. Yeah. Good. Okay. Good. Yeah. So and if I don't see your hand, just stop me. Okay. So anyway, the way I think about it, small scale heterogeneity, scattering studies, ultra low velocity zones, these very fine zones, not necessarily layers, or it might be global, tens of kilometers, hundreds of kilometers from things like these d double prime discontinuities that might be a manifestation of the phase change from Bridgmanite to post-perovskite, these blobs. On either side of it, I like to think of the core of the Earth has headphones, one under the Pacific, one under the Africa, Atlantic, topography. I could list as many other things, or show it in cartoon form, where you have, this is just the bottom of the mantle, these large low shear velocity provinces, and many phenomena that can get smaller and smaller scale. Now there's an observational bias when I make a cartoon like this, because that's pretty far away from our sources of energy near the surface and our recordings of energy. So what kind of attenuation happens? What kind of wave field distortions happen for us to be able to see or interpret something on our seismic data as scattering, or some sharp boundary to these big blobs, or anisotropy, or discontinuities that might be phase changes, and etc. There could be the spectrum of heterogeneity could be broad, even for these, we call these large low shear velocity provinces, these big things. These could have very fine scale structures as well. Just like, I guess, if we lived on the core mantle boundary and you tried to image the crust of the Earth, it might look like just this bland layer, but we know topography at the top and the bottom of the crust are exotic and rich in spectrum. So on spatial scales, we have things from kilometers or less. This is the core mantle boundary. There's no axis here, and actually that's perfect for my point. I could say whatever I want. Or large scale structures like these large low shear velocity provinces, which are really, they're continental in scale, at least the way we image them now. Or you could think about things in terms of temporal scales, we have things from the whole Earth itself oscillating in fundamental modes, and these are almost an hour long, the fundamental, mode of the Earth, that kind of spherical harmonic thing, or going to ambient noise, hertz, tens of hertz, to what we hear. Maybe this is too high, 1,000 hertz, 5,000 hertz. So I kind of view this as a scale in seismology. So we have kind of a broad range of temporal and spatial information. And the information that gets used kind of depends upon the target or the scientific question you're after, combined with how good are our data. So there's always like, oh, these data are applicable for this. Like data from the moon are really crappy, so you can only do so many things with it, but we still try. Okay. Okay, so just briefly, again, seismology in a slide, source, path, receiver. This is my, if I could only show you one slide and say, what's seismology? You make some energy, it travels, and it wiggles some devices, and we record the energy. Let's do that one more time because it's so fun. This is like, there we go. So, so you generate the energy, it propagates, we record the energy, and these recordings tell us about, information right at the recordings. They tell us about the path and structure along the way. They tell us about the nature of the energy. You want a movie? And so sources of energy, again, it's anything that causes vibrations. We call that the source. And I'm weaned a little bit traditionally from a seismology program, and so that's often earthquake. But it's any kind of vibration. Now, seismology is really kind of branching out, where these other fields, these have been going on for a while, but so the Earth interior investigations tends to be earthquakes or ambient noise, and you'll hear about that next week. There's cryoseismology, helioseismology. There's stellar seismology even. This is using not vibration, it's electromagnetic. Forensic seismology, trying to decipher what happens in some places. You can go there. I could add more to the list. In terms of using earthquakes, they are in specific places on the planet, and this is all of this is generating energy, and we can record these things. And this is, we all know this, but it's good to remind ourselves that they happen in specific places, and this has helped us understand the shapes of tectonic plates in places we can't quite get to, and volcanoes happen along these margins as well. And so, and seismic sensors tend to be on land. Of course, we are moving forward to try to get them in oceans. It's really expensive, and there's an engineering challenge there. But we would like sensors everywhere on the planet to illuminate the medium. The other sources of energy beyond earthquakes, I mean, we have internal and external and mixed. And, actually, this list can go on now because this is from a book that's maybe 20, 25 years old. But all of these things generate energy, and that energy can be used to study the source of the energy as well as the medium, whether it's atmosphere or Earth. So, one way I like to think about this is in terms of equilibrium, disequilibrium. If a medium has stress, and the crust of the Earth has stress, and we don't always know the state of stress. It's really hard to know throughout the crust. But there's stress, and when that stress overcomes the strength of the medium, something happens, and something breaks. And so here's our little block model of this, of three fundamental types of motion, but it's all basically the stress overcomes the strength, and boom, you have movement. And so these different kinds of stress will cause the shaking to go certain ways. This, of course, is a bit misleading, misconception. An earthquake is not a dot. And the slip is not a plane where it's uniform everywhere, but this are Geology 101 textbooks. And so these make these different kinds of faults. And these have to do with tectonic settings, so there's some relevance here from our tectonic plate boundaries of divergence from tensional stress, convergence from compressional stress, and transform boundaries and shear stress. These things can be combined in interesting ways, but this is kind of a tectonic source of stress that makes these things. And if we go to the wave paths, the word path is used differently by different people, but it's simply described as, some geometrical description of the energy from a source getting to your sensor. And there is a wave path, really how the vibration is propagating in the medium from, there's a source here, and these are time slices, and the darker colors are, of course, higher amplitude of these waves propagating and then bouncing, and so you can kind of track these guys. So this would be a wave path, a wave front, a propagating wave, however you want to word it, description of this wave moving. Often we talk about the perpendicular to the wave front, and you can connect those up, and we call that the ray path. And so the ray path is just a geometrical construct. It's much easier to draw. I can draw my ray path of something that bounces off the core right here, and I'm done. That would be a lot harder to if I were to try to legitimately draw the wave fronts and then, and so on. So in a lot of the diagrams we Earth interior seismologists show, we have these just the ray path, and we don't draw this complicated stuff. Sometimes we show both. So you have the wave fronts and the ray paths, and the geometry of these things, whether they're curved or not, has to do with the speeds, the wave speeds in the medium, obviously. And you probably all have seen this, but there's something that's very powerful here, just using Snell's law, that physics 1, we've all seen it with index of refraction in light, that if you have, constant property mediums here, a few layers, you kind of have our seismic index of refraction in our elastic medium, and this is predictive for computing the angles that the rays bend. In this case, the velocities are increasing with depth of the waves, and so you have this relationship of the geometry, again, of the ray path. I could just have straight lines if you wanted to see the plane waves in these constant property layers. And since it's constant along the ray, we give it a name, a ray parameter. So it's very simple, right? It's Snell's law, but it's also profound that you can describe the path that energy leaves that new Chalcedonia earthquake this morning, magnitude 6.5, to get to the Alps here with a single scalar thing, which it has to do with the angle that it departed at the earthquake to get here. And so that's kind of cool. So we often talk about ray parameter in doing this stuff. So that's probably the only time I'll do it in this lecture, but it turns out to be very convenient for us. So again, these paths are curved depending on the medium, and generally the velocity increases with depth in the planet. And we'll present these this concept of velocity depth in the planet next time, Jimmy. So not this time. I'll talk about Prem next time, in case you wanted to do that. So anyway, S-wave paths and P-wave paths, they're a little bit different from each other because the velocities are different, obviously. And so here you have a ray path representation of energy getting to different places. There's a few other things and some of this stuff is just for your reference, right? So again, takeoff angle. If you know this angle from any spot, in this case, hypocenter is where it starts, epicenter is at the surface. You can predict where it's going to end up. And we often talk about the Great Circle path or the Great Circle plane, the plane containing the Great Circle path between the earthquake and the receiver. And it's just calculated simply from the velocity depth distribution. So you have body waves from an earthquake. They travel through the body of the medium, and surface waves, which are a function of there being a sharp contrast in properties. Any place in a medium where you have strong contrast in properties, even the core mantle boundary, you will get interface waves. And so the interface waves between the solid and gas atmosphere, that we call them surface waves, and of course there's the Love and the Rayleigh. So that's strong contrast. It's a bit vague, yeah. So strong would be a change in state from fluid to solid. In the case of the surface, I think they happen probably at every interface, even if it's a few percent, but they're very, very low in amplitude. So in the case of the core mantle boundary, going to the silicate rock solid to the fluid, wave speeds are almost a half for P waves and no S waves. You get these Stoney waves and then at the surface waves.
But the 660, I guess, so you say there might be some, but we won't be able to see.
Yeah. So we further, so these P waves and S waves, there's a particle motion aspect. Now here I'm operating in a Cartesian universe where plane waves are happening, and here's my P waves up here. P waves are faster, and S waves are back here. P waves, the motion vibrates in the direction the wave is going. It's kind of a longitudinal particle vibration, and the S waves are perpendicular to that. Seismologists describe the S waves in terms of the part that's parallel to Earth's surface. So as the wave's cruising along, and here's Earth's surface, maybe Earth's surface doesn't move, the wave moves. The vibration that's parallel to the surface we call SH, for shear horizontal, and the particle motion that's is in perpendicular to the ray path and perpendicular to the horizontal one we call shear vertical, and so SV. So you often see this SV and SH in seismology discussions, and that's convenient to in discussions of anisotropy and what's going on in the media. And the P waves, of course, this is very basic, but are for isotropic media are higher velocity than the S waves, because here you just have the shear modulus and density, and the shear modulus a little bit more than that, plus the bulk modulus. You can combine these things, because here you could say, wow, it's nice to have a velocity that is completely due to density and something's resistance to shearing. And this is mixed, so we can combine these things and define something, this bulk velocity, that's just a factor of a medium's resistance to compression or incompressibility and density. So seismologists often bring in this bulk sound speed. It requires knowledge of both the P and S velocity, though, and sometimes that's not so clear. Okay, so we have this, a ray path. We've introduced that. I'm not drawing the wave front. We have P wave motion that's always in the direction of the wave or the ray, and we have horizontally propagating shear wave, and that's SH, and the one that's perpendicular to it depends where you are, right? Because it's always perpendicular to the ray path. So that's everything you need to know about ray wave geometry. It's not actually vertical. So the V is a bit of a misnomer. That's true. It's always just perpendicular to SH and perpendicular to the wave path. So depending on where you are. We live on the surface. We put our instruments on the surface. So you could see here I have these other things. And so, okay, here we are on the surface. We have our local vertical. Actually, seismologists put it down into the earth, but that's okay. And then, so if I'm going to install a seismometer outside here, I may pick the local north and east-west and up-down for my sensor. So this gets into our next bit on receiver. So, and so we'll talk about that geometry in a second. So we often say receiver or sensor, but it's anything that measures a ground vibration, you know, whether it's this thing attached to my head is recording a pressure wave. We often do 3 orthogonal sensors together, so it kind of doesn't, if I have 3 sensors that are make an orthogonal pair, it doesn't really matter what geometry they are, and I can always decompose them into, like, if the wave's coming from over there, I could do a matrix transformation to point to that wave to hopefully decompose the P and the SV and the SH energy. So, and then a bit of nomenclature. In fact, I just saw a new video on Facebook from the IRIS Consortium, and they had this wrong. But Seismograph is this kind of archaic thing where you actually have the drum that writes. That's Seismograph. Seismogram is the in the old days, it's the piece of paper that has the writing. In the new days, it's some digital time amplitude information that we put on our screen or we print. And seismometer is the sensor, the device that is recording the ground motion. So seismograph is like the old thing. We don't have a lot of those anymore. They're all broken, and we're all too lazy to try to fix them because it's like this old analog stuff. And it's funny, you have to go from digital to something that makes voltage to analog, and then attach it to these things. We used to have one at my place, ASU, and it's too much work to, like, you go digital to analog a bunch of times in order to get an old drum to turn and write something. So back to this geometry thing, and maybe this is too much detail. I'll try not to torture you too much, but we have an earthquake. Now imagine we're looking at the surface. We have this great circle path. I say great circle because it's the path that includes the center of the planet, which is different from a small circle. And then we have our, north, south, east, west stuff. But I really want to look at the information rotated to this thing, because we have this energy leaving the earthquake in my 2D world here of SV, SH, that's right, and our P motion going there. But I have kind of some seismometers that way. So we do this decomposition, just like I said, a quick little matrix rotation to get the energy from our instruments into this system. Oh, okay, I'm halfway through my slides. Let's see, what time is it? It's, oh good, so I'm going kind of fast. What? No, actually I have an exercise we can do at the end. If I go through my slides too quickly, we're going to do an exercise. This is my most meaningful slide. Anybody want to stand up and forward bend, some downward facing dog? Not in a lot of room. Put that camera away. Too late. It's already on Facebook. Well, I forgot I'm being filmed. Okay. Data or data. Do you say data or data? Data. Données. Now in English, many of us native English speakers still screw this up. Data, am I supposed to say ARP? Data is plural. Datum is singular. So if I have a lot of data are good from this earthquake. So anyway, so make sure in your papers, data are, datum is. Okay, so this is recordings of ground vibrations at some location in the case of seismology, studying earthquake stuff. In the case of, if we have sensors inside this building because we're in earthquake country and we want to see if it keeps its integrity, it's recording building vibration, not ground vibration. So we're usually talking time amplitude. So time's going this way and we have some amplitudes here of data. These are real data. Actually, and there's another thing. To say real data, is annoying to some seismologists because data are always real. And synthetic seismograms are, you could call that data prediction, but anyway, I digress. So we have body waves that go through the body of the planet, P waves and S waves, in all of their paths. We have waves on the surface. We have interface waves in the interior, and Stoneleigh waves are the name after the scientists who pioneered those. We have the actual oscillations of the planet itself, and you can call those modes, and there's many of them. We have ambient noise now, and you get a nice exposition on this next week from Pierre, which are becoming increasingly important, where we don't always have earthquakes. Now, we use this word phases loosely, and sometimes it's a bit confusing because what does that mean? But we generally use the word phases to describe the waves that take different paths, so we're going to give them special names. And they're named according to where they travel and what they bounce off of. And so we call those phases. And there are P waves and S waves, right? And so, but that's also a phase, because a P wave just didn't bounce off anything. So that kind of gets confusing. So we're going to quickly review the naming convention, and then you have it on slides here in case you haven't taken a seismology class. But it's almost like a genetic code or something. It's like everywhere the wave goes, it gets a letter. So if going through the mantle, not bouncing off anything, it's a P for a P wave and an S for an S wave. If it goes through the outer core, it adopts the capital K for the German word for core, which is Kern. And because a German discovered the core. There's no S waves in fluids. You can't sustain shear in a fluid. The inner core gets a capital I. I never thought, is that for Ing? Layman? Is that why they did I? Yeah, inner. And J, it's a very controversial J to see an S wave in the inner core. Actually, it's not controversial for some, but it's very hard to see. If you reflect off the core mantle boundary, doesn't matter what the wave motion is, it inherits a little c. If it reflects off the inner core, it inherits a little I. Now, if this is the surface of the planet and my earthquake's here, all of these things I've been talking about is energy that leaves the earthquake and goes downwards. You could also go up and hit the surface. I'm not telling you what this depth is. It could be 100 meters or 100 kilometers, right? If it goes up and hits the surface, we call that little p or little s. And then it goes on its merry way and collects its letters, okay? So this is the basic stuff. So for example, and stop me if you have questions. This is just, here's P wave. It didn't do anything. It went down as a P and got somewhere. So it just has its letter P. The red ones, though, bounced off the core, and the core gets its little c, so P, C, P. Simple, right? So every little thing, it just gets another letter. Now, if I drew the waves going up and then going down and bounce off the core, we would literally say little p, PCP. Or like S waves. These are really good for studying upper mantle and discontinuities and so on. If it's just, if it goes and that's an S wave, that would just be S. But, oh, it bounces and keeps going, so that's SS. So, yeah, it's simple. We get lazy. I don't want to write S, 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 S. Make me crazy, so we just put a number. So if something has a lot of bounces, we just put a number indicating how many legs. Or what about an S wave that goes down and turns into a P wave for the core and comes back? That's our SKS. Or if it bounces off the inner core, we get the baby I, the little I, SK, little I, KS. It's literally how we say it. Okay? Or you can start getting into the exotics of something that goes into the core and bounces a couple times, so you have 3 legs. That would be S3KS. You can go both ways, and so this is something that we talk about. Minor arc is the one that is less than 180 degrees. Major arc goes a long way around the planet. And this is a body of information that has largely been ignored in seismic tomography, and it's a huge source of information, and I'll talk about that in a couple days, because I think it's a powerful use of information we've been leaving alone. Or if you're studying the inner core, heterogeneity, you know, anisotropy, inner core, whatever, then you have to get into this. Really, it's P, K, capital I, K, P. Now this is the inner core waves, for some reason, and it's historical, they call PK, big I, KP, has just been given PKP. Actually, so there's and even without this thing, we just call it, sometimes people just call it PKP, means any P wave that gets into the core, inner core or outer core. And then the inner core ones also have this, this subscript notation to have to do with the wave having different parts. Like there's 2 waves in the outer core, and so it's something called a triplication, which I'll talk about in a minute. So seismologists are often loose about this, and it's probably the same thing I feel suffering when I see geochemistry and they keep changing the ratio. Is it He3443? And you know, I haven't learned intuition on those things, so it makes me I'm like, wow, I just thought I knew how to think about it, and now they're changing the axes and the numbers. But so we are I can explain those in more detail if you want, but it comes from something like this, and this is just Seismology 1 description of this. When you have a layer over a higher velocity layer, we say layer over a half space, you have the wave that can be a direct wave, a wave that can be a reflected wave, a wave that could be a refracted wave or a head wave. And then in travel time space, this is distance and time, you have just the direct wave is a straight line and constant velocity stuff. The reflected wave is a hyperbola. So this DF thing, when there's this thing which we call a triplication, because you have 3, so the tri, we put A, B, C, D. So this is a simple triplication. It's only A, B, C, D. So you might talk about the AB or the CD or the BC. And so when you see these PKP waves, there's a AB and a BC and a DF. It has to do with this kind of phenomena, but it's because of structure in the core. So you could put the letters there or not. But anyway, it has to do with that. Yeah, well, yes, that's right. You would have different names. And so it really depends on the situation and the velocities being used, because these triplications they can actually be born from just a change in the velocity gradient. And that happens in the outer core with the P waves. So you have these A, B, and BC. Okay. Do we need to do more yoga? Record sections. This is just a name for showing data with distance on one axis and time on the other. We also, seismologists sometimes call them profiles of data. Now, Pierre, is there another word for this that you use? Record section or section? Yeah, section. And then we have something so this is data. And then we have the travel time curves, which are the predictions from ray tracing codes. And these just use standard velocity versus depth reference surf models. These predict the arrival time of your seismic waves of interest. And we call those travel time curves. So I'll show you some examples. So here on the left, these are real data. As I said it, these are data. These are data. Authentic. Authentico. And this is, let's see, about almost 2 hours of information after the earthquake origin time. So it starts at like 500 seconds after the origin time. And this is distance. So 0 means I am at the earthquake. 180 means I am antipode on the other side of the planet. And these are SH data, so horizontally propagating, perpendicular to the path, parallel to the surface. And so we see the S wave very strong here. And these are the predictions of the travel times. So here's the S wave. I could plot it on top if I wanted. And then you get to a certain distance and it's starting to diffract around the core. So you can see the S wave and a little bit of diffraction. And you can see all of these lines, right? That means, okay, this is some distance at 80 degrees. I didn't, do I say? I don't say. I think this is in Tonga. And this is global data. So let's see, we're probably somewhere here, right here in the Alps, in southeast France, somewhere around here. So all of this energy is getting here, and so these wiggles are cohesive, and these are things that like this is do I overlay these guys? Anyway, it's impressive, right? These are things that went the long way around the planet. This is like an S wave that has bounced, 6 legs of an S wave going from Tonga the long way around the planet. Boom, 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 boom. And the southern hemisphere is really poorly covered in tomography models. So so these data can give light to that. So if we zoomed in on one of those zoom boxes here, you can see these guys. These are each one of these wiggles is all of the data were summed to just as being lazy, plotting every degree. But yeah, you could see these wiggles of the direct S wave and multiple S waves bouncing many times. Or this stuff back here are the ones that went the long way around the planet. And yeah, if your earthquake is strong enough, there's so many paths that the energy take on the inside. And it's powerful for understanding the Earth. And this stuff is virtually unused right now in Earth imaging. So it's kind of an area of research I'm trying to push forward in. If you Google travel time curve, you'll see something like this. This is probably 50 years old, but it hasn't changed. If you make the predictions today, maybe they shift a tiny bit because we used Prem and they used Jeffrey Bullen's model, which is from 1949. And there's no set convention for like, is the distance down here, or is the distance up here, or is the time down here? But basically it's time distance. So you just make sure you look at which axes are which. And there's many predicted exotic paths here. But now you're equipped. I could like tell you, Gaspar, draw me PKP, PKP. Come to the board and do it, right? And you could do it, right? Say yes. If you say yes, I won't make you come. What? Yes? Probably. Remember, it's like P, K. Actually, it bends down because it's a velocity decrease. K. Now, I didn't say I or not, but they were lazy back then, so it probably has an I. K, P. But there's 2 of them, so I have to keep going. And so it comes back for the other P, K, I, again, K, P. So yeah, so I mean, you can do it. I'm so moved. Okay. So for any earthquake that happens, you can go now, this thing called event plot, which is kind of cool, to IRIS. And we could look at, now that you've seen this stuff and you understand travel time curves and all of that, we can go to this earthquake this morning. Yeah, so this is the one that's just this morning. 6.4 southeast Loyalty Island. That's down here, right? Boom. And so IRIS built this kind of automatic thing based on this thing that my group made called Dude, which was, do you know this English slang for duct tape? Well, it's not slang, it's the stuff that you can fix anything with. We talk about using duct tape in our codes. That's like dirty, but it works. So it's like discovery using duct tape excessively. That's dude. And so, because so many seismologists now look at their one wave of interest, like, oh, I do anisotropy of the lithosphere using SKS. So I collect the data, I window around it, and we don't know actually was it a good earthquake? Were there other things? So these are all of these 1,000 probably something seismometers for this earthquake. Now these are the travel time curves for this earthquake. Now they have time and distance, and they plot distance opposite from how I do, but that's okay. So here you see the P wave, and somewhere around here they'll probably plot the travel time curves on top. Yeah, and there's some filtering. They like are just showing us some bandwidth. But anyway, you can go and figure out who's who in here. Like, oh wow, what's this guy here? We can go and that's PKP and PKIKP. And if you keep going this way, it's the one that bounced off. So this earthquake is showing all of that stuff. And they have many things. And if you're, maybe you want to know about the earthquake source, this is some distance where they had a lot of data now recorded in Alaska, where the transportable array is of EarthScope. And they can sum all of these guys. And this is what this earthquake looked like. So it's a 6.4, 90 degrees. So it's complicated, right? There's some crazy stuff going on. And so what of this crazy stuff is the source? What of this crazy stuff is the LLSVP between the Southwest Pacific and Alaska? That's what the seismologist plays with. Anyway, this event plot stuff is cool. There's, let's see, these ground motion videos. So if you have to teach general seismology to students or non-specialists, let's look at this earthquake. These things are cool. You could say, oh, it's right now it's just focused on the US, which is boring because the stations aren't that full, but you could see the colors are up and down. Let's go to the Rayleigh wave. Maybe, let's see, there we go. So maybe you can see further away from where you are, you can see the motion of the wave going up and down because this is slower, so I can't see it. Let's do this. They have these big ones that they've made where they've combined different earthquakes over time. It's that's not what I wanted. Let's go here. I'm getting some sunlight here. So this is a combination of a bunch of earthquakes in Baja California going across the US. And it's pretty powerful. You could even see the difference between you know, these beach balls, we call them, are like focal mechanisms, and I don't really have those in a lecture, but I can talk about them. You could see the difference. You can see the boundary between them right here, where it's like where the red and blue meet. It's opposite because you're crossing the quadrant. It's really cool. Anyway, I digress. Let's get out of this. Okay. Some deep earth data and their utility. So this is just going to be brief. I'm not going to show results from this stuff. I will talk about some things that are out there in the literature now based on different waves another time. But energy that bounces off the core, we often use it in a differential sense compared to the one that went through the mantle. And they're really good for heterogeneity down there, just general heterogeneity if you're trying to map large-scale stuff. Or anisotropy, SCS, is probably the most commonly used wave right now for D double prime anisotropy, because it goes and bounces off, and we can compare it to the S wave. We make corrections for what's going on up here or what we think. Or discontinuities, and some of the structure sorts of things that come out of these waves are the discontinuities, plausible phase transition, ultra-low velocity zones, large-low shear velocity provinces, scattering, core mantle boundary topography. It's powerful when you reference one wave to the other wave because the earthquake source, where it lives, is a model. We don't really know where the earthquake happens. We need to know the medium in order to correctly identify where and when the earthquake happened. And we don't know well, we have standard reference models for where the medium, the speeds of the medium. And so if the earthquake is off, even by 10 kilometers, that means this PCP wave has the wrong time. But if we reference it to the P wave, then that error is minimized because they both have the same error, so you difference them. Similarly with structure at or near the receiver where the heterogeneity is the strongest, if we do differential analyses, we're better off. Okay, diffracted waves, they were really in vogue like 30 years ago. And then there were not enough data to really do some great things with them. And so this is, I would call it low-hanging fruit. It's just waiting for people to get back into these things. And so, because they take these long paths, and I think of them as the deep earth equivalent to surface waves. Surface waves take these long paths to the surface. They average all kinds of stuff. But if you have a lot of them, the crisscrossing of these surface waves is kind of powerful for mapping the interior. So these are for heterogeneity, anisotropy, ultra-low velocity zones, ULVZ, LLSVPs. This LLSVP, I'll talk about this more in the other lectures. Large, low, shear velocity provinces. They're also present for P waves, large, but no one says LLPVP. I think we should just call them LLVPs, which I've advocated in some papers, but some of my seismology colleagues get a little mad at me because the shear wave drops are disproportionately larger than the P wave drops, so suggesting possibly composition. So they're trying to say that these are low velocity zones and they're really low for S waves, but whatever. Okay, so these guys are really pretty powerful, and they kind of blanket the core. Surface reflections are also great. They've been used for upper mantle things like if you have strong contrasts and properties, you act like the upper mantle discontinuities, the phase transitions from in the olivine system, olivine going to Wadsleyite, to the Spinel structure, ringwoodite, then to the perovskite structure at 660. Seismic energy bounces off of the undersides of these things. And so they're a little bit weak, but you can sum them up and make inferences about these boundaries and how they're higher or lower. And it's almost called the thermometer of the transition zone because these guys can map these boundaries, they depend on temperature. So anyway, this wave has gotten a lot of attention over the past few decades, especially the past 15 years. It's been used a lot to map the upper mantle. And you can see this wave also travels into the lower mantle. And if you go far enough in distance, this wave actually gets into the lowermost mantle. And so we've been actually collecting and measuring those to study the deepest mantle. But it's one of the biggest waves on the seismogram for S waves at large distances. So it's powerful. And this is a subjective collection of waves I'm showing you, but these are common ones that are used these days. There are the waves. Now, one topic that's been kind of resurrected of interest in the community for various reasons is what's going on right beneath the core mantle boundary, right? Is there chemical stratification? Is there some diffusion from the mantle to the core? This sort of stuff. So, well, if you want to look at that, a wave that spends a lot of its life right there is what you should study. And so this group of waves, SKKS, SKKK, 3K, SKKKK, 4KS, these have been used, and there's even 5K. And so these guys bounce under there, and they're studied in a differential sense. This guy compared to that one compared to that one. And these are the best things for studying right beneath Earth's core mantle boundary. And there's a challenge in which the community has basically been ignoring. And so those of you who are not seismologists, if I am at a conference and I say, oh, we have this great new discovery of beneath the core boundary using we talk about these guys all together as SMKS, to M being any number of the multiple core segments. You should stop me and say, what have you done to demonstrate that the base of the mantle is not affecting your waves? So remember that, make note. Bother the seismologists who say they've imaged the outermost core with what about the deepest mantle? Because D double prime, the base of the mantle, is more heterogeneous than anywhere on Earth except the outer shell of the planet. So as soon as you get below about 1,000 kilometers, it's pretty homogeneous. There's heterogeneity for sure, but when you get to the bottom, it's strong. That's way stronger than anything deeper down. So that's gotta change. Remember, if the velocities change, the ray paths bend accordingly, and so that's going to change the nature of those waves. But anyway, these guys are great. They're really fun to study, and yes.
I was wondering how hard it is to pick those exotic phases off a seismogram. Can we be confident that we can actually pick those things? Because they're pretty small amplitude.
Yes, we can be confident, and yes, they're small amplitude for some data. But these data are if the earthquake's strong enough, and there's another little hidden secret, we like earthquakes where the stress drop happens right away, so they're kind of impulsive, because some of these waves get close together in time. If the earthquake's big and it's not very impulsive, then this source time function overlaps with the next waves, and it's just a big blur and you can't do anything. So you can see these on single seismograms for really good earthquakes. Now, what's a really good earthquake? Maybe you have a 10% success rate for that sweet spot magnitude range for these waves. However, and Pierre's going to talk about this in detail, the array processing, where if you have a bunch of seismographic stations, you could sum them on the predicted travel time move out of that wave and bring the signal out of the noise. So in terms of like voodoo science that seismologists sometimes do, I would not put the SMKS waves in that category. So these ones are okay. Actually, not to dismiss my colleagues and former students in my own work on these. These are more in the voodoo science category because you actually have to, you take a geographical bin and you might have to add 50 of them together to really get these precursors to that wave from these bounces to come out of the noise level. So there's more of an averaging. It's not voodoo, it's just that there's a little bit of averaging because we're adding a bunch of information together. And how am I perhaps smearing my view? Because, it would be like taking 100 pictures of something that's a little bit out of focus, but then if the noise is incoherent and the signal's coherent, it starts poking out of the noise level. I guess you could, maybe Jimmy in his lecture later will talk about X-ray diffraction and sometimes these little peaks on the shoulders. You're like, I don't know, but if you added a bunch of them together, it's robust, right? Okay. Good, so I don't have to read your papers. No. So these are actually okay. Now, as you start adding bounces, you're getting more into the prayer category, right? I'm hoping it works. And
On the other hand, I mean, when you go to higher altitudes,
yes.
the path in the, at least on the mantle side, gets closer, so somewhat you're decreasing the problem.
Okay, so Stefan's talking about yes and no way. So he said, like, as yeah. No, but that's even if they were grouped on the exit, because we're usually looking at one of these guys compared to one of these guys. Do I show them? No, I don't put them together. Here, I have another plot on another day with them together. So the bundle of rays are very close together here. And so and this is often used as an argument for the inner core waves of PKP in the different branches, like, oh, it's only 500 kilometers apart or 300 kilometers apart. There's two things. One, the heterogeneity is at tens of kilometers for some of these waves. Just ignore that. If I have two waves coming down here really close to my core mantle boundary, and I could say this long wavelength heterogeneity, I'm immune from it because it's not going to separately affect these. But what happens is if there's a smooth lateral gradient, to get to my station, if I have a lateral gradient, these guys have to have gone a different place to get there. They stay together. They're not differentially affected in time by the structure here, but their paths can be perturbed. And that path can be different enough that now the differential times are bigger. Because it's almost like mapping it to effectively a different distance. And so you can get heterogeneity in each one of these, a travel time perturbation, because this ray bundle now has shifted due to a smooth gradient going into some anomaly. So we kind of sweep that under the rug. It's in fact, I have like a paper in like 1995 that's been referenced like 5 times that documents this, and no one references it. They're like, whatever. So seriously, it's really, I mean, I laugh, whatever. The core waves, now this is where I'm putting the initials here for the AB, and the gradient in the core changes. There's an interesting caustic. You know, when you look at your beer glass and the light's shining through and the reflection on the table has this funny bright spot that looks like a stoned butterfly? That's like a caustic. The same thing happens in the middle of the outer core with the energy. And so one wave kind of departs and you have these different paths. In the deeper core, this is a different wave. And so you have these different guys to study the inner core for the heterogeneity, the anisotropy. Is there an inner core? Does the inner core have topography? You can add the wave that bounces off. So that's pretty cool. So here you have the bouncing one. Sometimes this one that bounces off the inner core is referenced to the one that bounces off the core mantle boundary. And the timing difference of these guys with some assumptions is used to map the topography of the core mantle boundary. And that's a very difficult task because it depends on what do you know about the mantle, and you have to correct for it. And a testament to that is if you took the 10 or so maps of the core mantle boundary and compared them, there's a lot of divergence in the different solution models, which means it's really hard, and seismologists aren't necessarily agreeing in their answers. Okay? You could, anything that travels in the D double prime, I loosely call D double prime just the bottom hundreds of kilometers of the mantle. It doesn't mean anything structurally. It's just a depth shell. Anything that goes in that lowermost mantle depth shell, and these are the 3 S waves that do. Remember, they have particle motion that is S waves that are perpendicular to the ray path, or also perpendicular to it, but in the horizontal direction. You could decompose the wave field when it gets to your sensor into these two, and to see if these two guys have separated. Because if I have anisotropic medium here, remember, anisotropy is not isotropy, and isotropy, iso, is same in all directions. So that means my wave speeds can depend on the direction of propagation. So these guys are used, sometimes it's complicated with assumptions, to demonstrate that the base of the mantle has propagation direction dependence. So anisotropy. And so that's, it's fun, it's really hard. Every 10 years I get excited about working on these things, and then I kind of think like, wow, I don't believe any of it. So I publish paper, and I get kind of disillusioned and then drop it for 10 years. I'm about ready to do something again because it's probably been 10 years. I think 97, '07, I'm not sure. I don't even remember, I blocked it out. So if you want to, this is just using GMT, the generic mapping tools freeware package. You can go to my website, and I have a little script in here, a seashell script. It's really kind of archaic and ancient, but you should be able to modify it to make your own ray paths for these different things using the Tau-P toolkit and GMT to make your own. And so, or if you want to take these and just alter it, you can get the PostScript or Adobe Illustrator version and play around. So there's lots there. Okay. So there's some paths in the Earth, and you can look on the seismogram, you can make some predictions. And so here we are. Here's a wave that has bounced off the core, and it gets there, and maybe there's some wiggle. And maybe the wiggle gets there when you think it is, and so you're like, oh, okay, everything's great. But that actually almost never happens. I don't think I've ever measured a wave and the travel time anomaly is 0.0. So usually it gets there, and the amplitude's modulated, and the time is modulated. And so I'm like, okay, cool. I have some kind of modulated time. We usually take the difference, and we work in these things we call residuals, which is observed minus predicted. And that's when the seismologist starts having fun. Maybe it's like, oh, it's this, some shape in the mantle, and that's where I accumulated some time anomaly from something like that. You know, it's on the seismologist to demonstrate where the anomaly is, how big it is, you know, is it a constant property, whatever kind of thing. So you need more than one ray path to distinguish from where you accumulate this time anomaly. So that's a lot of seismology right there. Probably historically, it's probably like, you know, 80% of seismology is dealing with perturbed time from what you predict. The other part of it is you might see something you didn't expect, like, oh, here's a new arrival. In my reference model of the interior does not predict anything showing up here. So what could that be? And again, is it some reflection off of my little gummy bear here, or is it something having meaning in terms of our tectonic understanding of the interior, or interpretations of seismic tomography like we saw last night? Or is it, you know, little heterogeneities from some kind of thing? That, again, is has to be demonstrated by the study of which of these kind of cartoons might have meaning and be a constrained interpretation of the data. And this is kind of a theme that I really want to emphasize in these lectures, is that there's something that we start with. The ground vibrated a certain way somewhere, and we reference that vibration according to, okay, someone said the earthquake was here and started at this time, and I make a prediction, and I'm different from the prediction. So that's my information. And we take that information, and based on some understanding of the interior, we make some predictions of where things went, and then we go to the interpretation domain. And is the interpretation domain constrained or fantasy? Hopefully the paper that we read, the publication, lets us kind of decide, you know? So any questions about this?
I have one. You just said, oh, someone told me the earthquake happened there and that time.
Yes.
So I guess to do that, you actually have to use the seismometers, and you have to propagate these fractions. And of course, it's affected by the structure. So is there an issue in it?
Yeah, so Stefan pointed out that I said someone gave me the earthquake location, and there are a few different groups or organizations like the Geological Survey, the U.S. Geological Survey, or the International Seismological Center, ISC, in England, or even some groups, Joran Ekstrom at Lamont, who publish, they take all the data that are recorded around the planet and they locate the earthquake with it. And there's some errors, and sometimes we don't know what the errors are in the earthquake's location, the focal mechanism, that is the mechanism of orientation of the fault and slip on the fault, which is all kind of comes out of this thing we call the moment tensor. If that is wrong, we don't really know, it's just how good are the data. But if that is wrong, then if I'm going to predict the time of a reflection off the core, it's based on where this thing is. And it's based on when this thing started. So there is always an uncertainty there. And so for that reason, we try to do differential analyses. And so if my earthquake started 5 seconds wrong from when it did, my P wave has that 5-second error. My PCP has that 5-second error. I subtract them, that error goes away. So, however, if you're taking absolute times like we do in tomography, they're all affected by this. So almost most analyses that don't do differential time stuff, they relocate the earthquake themselves. But there's a circular argument in doing that, because you relocate the earthquake using some structure, but your structure has been determined by earthquakes that are poorly located. So it's a circular thing. So everyone does their best to minimize the problem. And the more data we collect, if the origin time errors are normally distributed, maybe they start becoming less and less because your model gets better and better. But it's a problem. So that's a very good question. You should be doing seismology. Your weekends. Okay. So from data to interpretation, this is just kind of a little bit of a recap, because we start with, slip happens somewhere. And like I said, it's not like this. In reality, the earthquake is a slip distribution. It starts somewhere, and that slip starts propagating. So for very large earthquakes, it's complicated, right? Because if the slip starts here, and it starts slipping a lot, and then there's a little pause, and then it jumps and starts slipping over here. There's a time history of slip. And so if I'm looking at that earthquake here, or if I'm looking at that earthquake here, the nature of that slip distribution is different, right? It's almost like a Doppler effect. You can think about it. And there's some time history of the moment, the seismic moment, energy, if you want, releasing from this particular earthquake, and there's a model. So it's actually even a little more complicated than we may not know exactly where the earthquake is. If you have lots of seismometers in the vicinity of the earthquake, you can do a pretty good job of saying where it is. But there's a slip distribution, and it's non-uniform in space and time. So that's kind of an interesting component to that. For that reason, many of us who study the Earth interior using body waves, we tend to try to have earthquakes that are not too big, so we don't want super complicated rupture histories playing into it. So like this is a recent Fiji earthquake from, this is September. Yes? Yeah, exactly.
Even for small scale cases, it's going to be, you're only going to have like a direct, it's going to be not a discrete event. So how do you, because the recording of non-discrete events, you're not going to have like 1 P wave and more than 2.
Yes, so it's a really it's a really good question. So if my source process is at a time scale that is bigger than the timing I want to resolve between a pulse that went and bounced off the core and went through the mantle, then I'm going to have a challenging time. So this is a huge earthquake in that we have like 100-second source time function. On the other hand, this non-delta function process here, if the P wave gets there, and I have this 100-second complicated history just for the P wave, and 200 seconds later, I have something bouncing off the core, same complicated thing. I could use correlative analyses between the two, these two complicated things, to get the differential time, and it's okay. So it boils down to the, in my mind at least, what kind of timing resolution do you need between the different paths you may be studying and comparing to each other? I don't know if I answered the right question.
Okay, do situations happen where the time scale is okay?
Yeah, so, and I'll show you an example right now. So for this earthquake, it's kind of complicated. It's here, recorded at all these stations, and this is what the timing history looks like for a bunch, again, these Earth scope stations in Alaska. It's complicated. I don't like that. On another hand, so it's a large earthquake. Here's one for a smaller earthquake, also in Fiji. It's probably aftershock. This is kind of, and these are velocity recordings, which for a delta function, velocity recorder, you take a derivative of displacement to get velocity, so you have an up and a down. And so this is nice. So an Earth interior imager using body waves would look at this and say, these are good data, because it's a simple up and down, and it happens over some 5 seconds. Now I could do differential times even when the waves start to get closer. So we have earthquakes that we call like good data or complicated data. These are not complicated data. Does that help you?
Yeah,
Okay.
in most cases, P wave.
This is yes, this is a P wave. Yeah, this is a P wave.
The previous one as well?
Probably a P wave also, because this is out of that Iris data product. Yeah, this is also P wave. So.
For example, I mean, for the complicated case, how do you pick the P wave?
Yeah, because there's different ways to describe this whole thing as a P wave. What it is, it's a bunch of P waves from the source, right? Every little, if you want to think of the fault, if this desk is the fault plane, and you could discretize it and think of each patch as making its own P wave. But to answer your question, if I'm going to use this guy for travel time studies, I'm going to look at when do I leave this quiescence time and then energy gets there. So we typically look at the first arriving energy to say that's the fastest path. That's when this complicated mess got there. So if you and this plot is scaled by the largest thing. If you zoom in here, can you see this break? Yeah. So okay, so earthquake happens, and then the waves start to happen. They start rippling through the medium, and they get to our sensors, and we see these different things depending on where you are. Here's a P wave. Here we get farther, so it's a little problem with the gray patch. It's not supposed to be in the core. Anyway, the diffracted P wave. And so if the medium has heterogeneities, of course, we end up with some travel time anomalies. So the waves happen, and then we record them, and these are literally very sensitive microphones in the ground somewhere. Some cases they're permanent, some cases they're temporary, like this one, this University of Oregon experiment. They go out in Galapagos, and you put your instruments there, and you make some measurements. And there's thousands of sensors right now that any of us can get online and get for any earthquake. It's the seismologists tend to be a pretty open source community, so you can get online, download it. Look how happy you are when you get seismic data. So if any of you want to change your major, come to ASU and do a PhD. We'll be this happy downloading data. There's a lot of tools now that you can automatically bring the data to your local disk, and we make a lot of decisions actually. And this is just a random thing off the web. The processing stuff, mine aren't this complicated, but you have some recipe you're processing and filtering and stuff, and I'll talk about that next time. Then you do some analyses and modeling, and you get some results, like here's some tomography results. So this is this is a result of a mathematical inversion of the data, and there's lots of details before you get your colors, and then you go to the interpretation of those colors. And we heard a lot of interpretations last night, actually. So that talk kind of set up some things I'll talk about over the next couple days, like giant plumes and hotspots and yes and no, this, that. It's fascinating. So then you end up with different cartoons, and they're different. And that difference in the cartoons tells us something that, okay, maybe we don't have that so understood. So, but anyways, we start with earthquake, and we get some data along the way, and we make some decisions, and our model gets some answers, and then we have some fun. And so my point here is that there's many steps and decisions along the way to end up with our final story. And I tell my students that there's a culture to our interpretation, and it's really, I tell, okay, download the most recent 20 Nature or Science papers that have to do with geophysics. I don't care if it's phase transition source mechanism for deep earthquakes, or rheology, change, viscosity, whatever. Get them and look at the title, and how does that title relate to what they actually did versus what the model gave versus the interpretation. And that's an interesting, there's a culture to, and that culture is changing. I'd say 30 years ago, the titles of papers had more to do with what the scientists did. And now they're moving more to what the scientists are, the story, the interpretation. That's kind of interesting. So where are we? Okay, so today I tried to talk about these various things. We have these vibrations, there's lots of scales, big range of scales temporally, spatially. So the earthquakes are basically stress happens, and we have these paths, and we have all these names, and seismology kind of boils down to Snell's law. It's really kind of simple, unless you really want to talk about the spectral and amplitude component to the waves, then you actually have to use the seismic wave equation, which is, again, it's a glorified Hooke's law, F equals minus kx, that the elastic medium responds, and you combine that with Newton's law, F equals ma, so you have your kx equals ma, but the medium is not just, vacuum and electromagnetism, so you end up with this constitutive relationship, but it's still, I don't know, it's elegant. We record the stuff, and we have some geometry considerations, and then the waves get there. We have different kinds of waves, different kinds of energy that get used. We name them, and we predict them, and some waves are culturally commonly used, and there's more exotic ones that I think we need to get into, and then we do this interpretation stuff. And there's a lot of steps that if you're doing something that depends upon what the seismologist said, it's really important to be cognizant of these steps. If you're studying partial melt of ferropericlase at 120 GPa, because some seismologist said ultra-low velocity zones are partially molten. Well, the seismologist can't really say that. A seismologist gives velocities, and sometimes those velocities are assumed, like I'm going to assume the S wave drop is 3 times the P wave drop. Well, right there, you can't take that to the mineralogical domain. If the seismologist can prove that 3 times to the P drop to the 1, 3 to 1, and or whatever, well, do they give you the density, and is the density constrained? So all of that stuff is really important for you to keep in mind. The journey I took before I put something in a paper, if it's going to go to a non-seismological domain. And I argue that actually you bring the other disciplines of inquiry, bring information that could actually help the seismologist who's not necessarily aware of that stuff. So I think that's really important. And tomorrow is going to be kind of Earth interior modeling, examples of taking this kind of some of this stuff from today, and how do we turn that into some ideas in the single dimension, just velocity versus depth, or 2 or 3 dimensions, moving towards tomography. What are some of those steps and decisions and assumptions we make? Or, you know, a skeptic might say, you know, dirty secrets or dirty laundry. It's just we have to make some assumptions in order to get to the model. And what are some of those? So I'll try to demystify some of those, working our way towards models of the interior and our interpretations. Okay? And look at that, it's 10:15. Perfect. So, okay. Again, you can stop me and bug me or email me, whatever, for questions, if you have any now, or we can just as we go.
I noticed you call this transmission law Snell's law. I learned as a young student that it was called Descartes' law.
Oh, that's true. Yeah. So yeah. So we name everything. We rename everything. Yeah, like who invented the car in the first flight, and you know, sorry, it was like all these French guys did it first, but
No, I'm not saying that. Because I know, I mean, usually some people do put two names, and for example, in fluid dynamics, we have the Boussinesq approximation. Boussinesq was French, but in fact, nowadays most people say it's Oberbeck-Boussinesq because there was this German researcher that
oh, I
did
see.
that maybe 20 years before, in fact.
Mm.
So there's no direction.
Yeah, yeah, yeah.
I'm wondering about the Snell and Descartes.
Yeah.
Who did Snell? You mean or Descartes?
Good. Yeah. Yes. I didn't understand the beginning part. Oh, okay. Yes. I don't know. Like, so the iterative process of determining the source location, there, we have a medium. We make predictions of through the medium for some earthquake, and then we relocate this earthquake. I think a couple iterations is usually the location doesn't update so much, but it might depend. Different tomographers do it differently. Some people relocate the earthquake, then do the tomography. Some people jointly invert to find the location and the tomography at the same time. And so there's different philosophies on this. I think the joint inversion is probably fine. And then they iteratively do it. And then they have some measurement on how well the model predicts the data and what's the reduction in variance of the error. And when that stops changing, they're like, I'm done. And those decisions maybe are a little different between different imagers. Yeah. Yes? Yeah. Okay, that's a good question. So the energy, if the earthquakes are close, or if two earthquakes happen at the same time, the same distance away, and the same strength, you're screwed. It's just going to look like one strong earthquake, and the waves are going to perfectly combine. Usually, since the earthquakes are around the planet in different places, some earthquake is the strongest. In fact, one thing we do if we're using an earthquake is we make sure that no other earthquake happened within an hour of that earthquake that's at some level that this sensor in, you know, Hawaii or whatever can see. So if some earthquake happens very far away in the Mediterranean, Hawaii won't see it unless it's up to, say, magnitude 5.5. So so we're usually careful and just say, oh, 2 earthquakes happen in a close amount of time, and so we don't use either of them. But for these magnitude 4 earthquakes, 4.5 earthquakes, usually they're in the noise level. And if you have some magnitude 6.6 that happens in Kamchatka, and I'm recording that in the US, it's the biggest thing. And it's so much bigger, hundreds of times bigger than the little guys that are happening all over the planet. It's just like right now you guys could all be whispering and Stefan's talking to me and I can hear him. Garnero really ought to shut up, but I hear you because you're close and loud. So.
Is it also about combining different sources and different sensors? Because always, I mean, if your sensor is too close to a small earthquake, other sensors will be far away.
That's right, yeah.
So maybe you lose one sensor in the process.
Yeah, so that's right. If we're really desperate for that earthquake that happened at the same time, you could look at the data and just see, are these data behaving as predicted for that earthquake with the travel time curves and the raw data? And you could, yeah, no problem, this is good. And then as you get to the earthquakes close, the sensors close to the earthquake, you're like, no, don't use those. Yeah. Okay, café, s'il vous plaît. Okay, thanks.